You've heard the headlines: interstellar comet, strange chemistry, Harvard astronomer making bold claims. But here's what they're not telling you. In less than a month, 3I Atlas disappears behind the sun for 4 weeks. Total blackout. Every telescope on Earth useless. And during that window, if Avi Loeb is right, this object could maneuver, and we'd have no way of catching it in the act. The trajectory is nearly flat against the ecliptic, 5 degrees off in a universe of random angles. The carbon dioxide to water ratio is 8:1 when it should be the opposite. It's venting nickel without iron in ways our models can't explain. And it's threading past Mars, then the Sun, then Jupiter like waypoints on a flight plan. But here's what Loeb is really saying, and it's more unsettling than alien probes. This is about whether we can investigate anomalies seriously, whether we can sit with uncertainty without collapsing into dismissal or hysteria. And right now, we're struggling. We spent days analysing every observation, every spectrum, every trajectory model. We're going to show you what makes this genuinely different, what the solar conjunction blackout actually means, and why the next 4 weeks matter more than you think. Because whether this is the weirdest comet ever or something else entirely, how we respond right now is the test. Let's get into it. But first, if you're here for analysis that goes deeper than the headlines, hit that subscribe button and tell me in the comments where you're listening from tonight, and whether you think we are demonstrating readiness for the unknown, or we're just exposing how unprepared we actually are. Chapter 1. 3I Atlas is following a plan. Here's where things get uncomfortable. According to Avi Loeb, 3I Atlas trajectory looks less like cosmic chance and more like a carefully plotted course. Let me explain what I mean by carefully plotted. When the Atlas Survey telescopes in Hawaii first spotted this object in September 2024, astronomers immediately recognized something unusual. Most comets tumble into our solar system from random directions. Their paths tilted at wild angles relative to the plane where Earth and the other planets orbit. That flat disk we call the ecliptic. It's basically the solar system's highway, and most interstellar visitors don't use it. They're more like meteors streaking across lanes at bizarre angles. But 3I Atlas? It's staying in its lane. The formal numbers tell the story. This object has an inclination of approximately 175.11 degrees. In plain English, that means it's travelling retrograde, backward relative to the planets. But here's the key part. It's only about 5 degrees off the ecliptic plane. For a visitor from interstellar space, that's remarkably organised. Harvard astronomer Avi Loeb, never one to mince words, put it bluntly. This looks more like a flight plan than a random plunge. Now, before you think this is just one scientist's wild speculation, let me give you the hard data that proves this thing is genuinely bizarre. Its eccentricity is approximately 6. That's not a typo. In orbital mechanics, an eccentricity of 1.0 means you're on a parabolic escape trajectory from the Sun. Anything above 1 means you're hyperbolic. You came from somewhere else, and you're leaving again. An eccentricity of 6? That's like showing up at a party doing 90 miles per hour through the front door. This object came screaming in from interstellar space with enough velocity to prove, beyond doubt, it didn't originate in our solar system. The discovery was confirmed by multiple teams globally. Atlas in Hawaii spotted it first, reported it to the Minor Planet Center, and then observatories around the world swung into action. Pan-STARRS, the Canada-France-Hawaii telescope, professional facilities across continents, all confirmed the same thing. This is real, this is here, and it's heading for the Sun. Perihelion, the point of closest approach to our star, happens on October 29th and 30th, 2025. That's less than a month from now. At perihelion, 3I Atlas will be approximately 0.96 astronomical units from the Sun, inside the orbit of Earth. Its closest approach to our planet, about 1.8 astronomical units, roughly 168 million miles. NASA and ESA have been clear. There is no threat to Earth. The geometry simply doesn't allow for an impact. But here's where the geometry gets interesting for other reasons. The object's path creates a sequence of opportunities. On October 3rd, 2025, it passes relatively close to Mars, close enough that the European Space Agency is planning to aim the Mars Express orbiter and the Trace Gas orbiter at it. That's just days from now. Then comes perihelion, and then, this is the part that raises eyebrows, on March 16th, 2026, it will pass within 0.358 astronomical units of Jupiter. That's roughly 33 million miles from the largest planet in our solar system, Mars, Sun, Jupiter. 3 distinct vantage points, each offering something different, each a potential sensing opportunity if you were, say, conducting a survey. And sandwiched right in the middle of this sequence is the solar conjunction, the period when 3i Atlas passes behind the Sun from Earth's perspective. For several weeks starting late October, we simply cannot observe it from our planet. Hubble can't see it, ground telescopes can't track it. Even JWST, the James Webb Space Telescope, will have limited viewing geometry. If you were planning a course through the inner solar system and wanted a window where Earth's astronomers would be temporarily blind, you'd be hard-pressed to design a better scenario. Now, let's be scientifically honest here. A low inclination doesn't automatically mean intent. Interstellar objects have to come from somewhere, and if they're ejected from planetary systems during formation, they might naturally tend toward the disk planes of their birth systems, which could coincidentally align with our ecliptic. Selection effects also matter. We're better at detecting objects that pass through the plane where most of our survey telescopes are aimed. But here's the thing that keeps astronomers up at night. We've only detected 3 confirmed interstellar objects. 3 in all of human history. The first, 1I/Oumuamua, arrived in 2017 with a steeply tilted orbit and strange acceleration that defied easy explanation. The second, 2I/Borisov, showed up in 2019 looking like a normal comet but from interstellar space. And now 3i Atlas arrives on this peculiarly flat trajectory, timing its perihelion passage to coincide with solar conjunction when we can't watch. The orbital precision isn't the only unusual thing, it's the combination, the trajectory, the timing, the geometry. Avi Loeb describes it as a rail-flat glide path, followed by a sun eclipse. From a purely tactical standpoint, if someone wanted to approach the inner solar system while minimizing observational opportunities, this would be close to an optimal solution. We are creatures of pattern recognition. We see faces in clouds and agency in randomness. This is a good thing. It kept our ancestors alive. But it also means we must be cautious. The universe is not required to make sense to us, and coincidences do happen. Yet consider this thought experiment. Imagine you're standing in a field, and someone throws a dart from a mile away. The dart lands within inches of your feet. You'd be justified in at least asking, was that random, or were they aiming? 3i Atlas is that dart. And we're starting to wonder who threw it. The most critical window is coming. If anything unusual is going to happen, any course change, any unexpected behaviour, any evidence that this is something other than a natural chunk of ice and rock, it would most likely occur during the solar conjunction, the period when we cannot see, the silence before the sun. But before we get to that solar blackout, we need to talk about what astronomers have already seen when they aimed their best instruments at this visitor. Because the optics and chemistry of 3i Atlas are even stranger than its trajectory. Some comets glow. This one might have headlights. Chapter 2. Headlights in the Dark and the Nickel Anomaly. On July 21st, 2025, the Hubble Space Telescope turned its sharp eye toward 3i Atlas and captured the clearest image we have of this interstellar visitor. What Hubble revealed was both familiar and deeply strange. The good news? It looks like a comet. There's a nucleus, the solid core, somewhere between 320 metres and 5.6 kilometres across. That range is wide because Hubble is looking at a fuzzy active object surrounded by dust and gas, making precise measurements difficult. But the important part is this. 3i Atlas is small enough to be natural and large enough to be structurally significant. Hubble also captured a sunward dust plume and a faint anti-solar tail, the classic signature of a comet being baked by solar radiation. Gas sublimates from the nucleus, carrying dust with it, and solar pressure pushes that material away from the sun, creating the iconic tail. Later observations by the Gemini Observatory resolved an even longer anti-solar tail stretching behind the object. So, by all appearances, this thing is active, it's outgassing, it's behaving. But then Avi Loeb looked at the same data and saw something else. He describes what he calls a forward glow, a luminous region on the sunward face of the object, bright and directional, not quite matching the standard morphology of a cometary coma. To Loeb, this looks less like passive dust scattering sunlight, and more like something actively glowing toward the sun. He's careful to call it his interpretation, not established fact. Mainstream astronomers see a dust plume. Loeb sees headlights. Who's right? Well, that depends on the data you emphasise. The Hubble and Gemini observations do show tailing activity. There's no dispute there. But Loeb's point is about the distribution of brightness. In a typical comet, you expect roughly symmetrical glowing around the nucleus, shaped by the solar wind and radiation pressure. What he's noting is an asymmetry. More emission toward the sun than you'd expect from dust alone. Could be dust jets preferentially pointing sunward due to the nucleus's rotation. Could be surface features concentrating outgassing in one direction. Or, if you're Loeb, it could be active thermal management, an object deliberately venting material to control its temperature as it approaches the sun. Let's table that for a moment and talk about what the James Webb Space Telescope found, because JWST doesn't care about visible light. It looks in infrared, and what it saw in the coma of 3I Atlas is frankly bizarre. On August 6th, 2025, JWST aimed its spectrometers at this comet and analysed the chemical composition of the gas cloud surrounding it. The results were released on August 25th and immediately raised eyebrows across the planetary science community. Carbon dioxide. Lots and lots of carbon dioxide. Specifically, JWST measured a ratio of carbon dioxide to water, CO2 to H2O, of approximately 8 to 1. Let me put that in perspective. In most comets, water is the dominant volatile. It's what makes comets comet. They're dirty snowballs, after all. Water sublimates as they approach the sun, creating the coma and tail. Carbon dioxide is usually present, but as a secondary component, not the main event. A ratio of 8 to 1 means this comet is venting 8 times more carbon dioxide than water. That's not unheard of. There are rare comets with unusual volatile compositions, but it's definitely in the what the hell category of cometary science. Then there's Spherex, the spectrophotometer for the history of the universe, epoch of reionization, and ICE's Explorer. Yes, they really wanted that acronym to work, is a space telescope designed to map the sky in infrared. In late 2025, Spherex observed 3I Atlas and found something extraordinary. An enormous carbon dioxide coma extending at least 348,000 kilometers from the nucleus. That's nearly the distance from the Earth to the Moon. This object is wrapped in a bubble of CO2 larger than most planetary magnetospheres. And here's the kicker. Spherex did not detect comparable amounts of water or carbon monoxide at that same epoch. The carbon dioxide dominance isn't just a quirk of one measurement, it's consistent across multiple observations and instruments. Why does this matter? Because it challenges our understanding of how comets form. Water ice is abundant in the cold outer regions of star systems. Carbon dioxide can also condense there, but usually at slightly different temperatures and locations. A comet that's 8 parts CO2 to 1 part water suggests it formed in a very specific thermal environment, perhaps near a carbon dioxide ice line, or perhaps its surface was heavily processed by radiation in interstellar space, sealing off the water ice beneath a carbon dioxide crust. Or, if you're inclined toward more exotic explanations, carbon dioxide makes an excellent working fluid. It sublimates at lower temperatures than water, it's easier to handle in thermal management systems, and if you were designing a passive cooling system for a spacecraft approaching a star, carbon dioxide would be on your shortlist. But wait, we're not done with the chemistry weirdness. Enter nickel. The Very Large Telescope in Chile, using the UVS and X-shooter spectrographs, detected emission lines from neutral nickel atoms, Ni1, in the coma of 3I Atlas, at surprisingly large distances from the nucleus. Nickel emission in comets isn't unheard of, but it's usually faint and associated with metal-bearing dust grains being vaporized close to the nucleus by intense solar heating. What's strange here is the amount of nickel being detected, and the fact that there's essentially no corresponding ion emission. Iron and nickel are cosmic companions. They're both abundant products of stellar nucleosynthesis, and in natural, rocky or metallic bodies, they tend to appear together. You rarely see nickel without iron, yet that's what we're seeing in 3I Atlas. Strong nickel lines, weak or absent iron lines. How do you explain that? One natural mechanism involves organometallic compounds, molecules where metal atoms are bonded to organic carbon chains. Nickel can form stable carbonyls, compounds like nickel tetracarbonyl, which are volatile and can sublimate at relatively low temperatures. Under ultraviolet light, these molecules break apart, releasing nickel atoms that glow when excited by sunlight. Iron can do similar chemistry, but the pathways are different, and under certain conditions you might release nickel preferentially over iron. It's exotic, but it's within the realm of known chemistry. Avi Loeb, writing in late September 2025, highlighted what he called extreme nickel production, as 3I Atlas moved from approximately 3.14 astronomical units to 2.14 astronomical units from the Sun. He noted the delayed emergence of iron lines, and suggested this could indicate non-thermal or even engineered heating, a controlled release of materials rather than passive sublimation. That's a hypothesis, it's not established fact. But it's a testable one. If iron emission starts appearing as the comet gets closer to the Sun and hotter, that would support the natural organometallic explanation. If iron never shows up, or if the nickel-to-iron ratio remains bizarrely skewed, well, that's harder to explain naturally. Let's synthesize what we have so far. 3I Atlas shows a potentially asymmetric forward glow that Loeb interprets as sunward, a carbon dioxide to water ratio of 8:1, among the highest ever measured in a comet, an enormous carbon dioxide coma with minimal water or carbon monoxide detection, strong nickel emission without corresponding iron, suggesting unusual chemistry or unusual heating. None of these things, individually, is impossible naturally, but together, this is not a textbook comet. This is an outlier among outliers. The competing models are essentially two. Model 1, 3I Atlas is a natural comet with an unusual formation history and exotic chemistry, behaving in ways we don't fully understand yet, but that are consistent with known physics. Model 2, 3I Atlas is something artificial using solar thermal energy for power or propulsion, venting carbon dioxide as a working fluid, and outgassing nickel-bearing materials as an incidental byproduct of its operations. We don't have consensus. We don't even have a peer-reviewed explanation for the nickel-iron decoupling yet. What we have is data that doesn't fit comfortably into our existing boxes and a ticking clock until the object disappears behind the Sun. The question hanging in the air is this: are we looking at the universe's weirdest comet, or are we looking at technology? And if it's technology, whose technology? That's where the Loeb scale comes in, a framework for quantifying just how weird something is, and whether weird crosses the line into artificial. Because when you're dealing with interstellar objects, you need a system for keeping score, otherwise you're just shouting opinions into the void. So let's talk about how you score a cosmic mystery. Chapter 3. The Loeb Scale and the Technological Spectrum. Imagine you're a detective investigating a break-in. You need a system for evaluating evidence, fingerprints, motive, opportunity. In astronomy, when we're faced with objects that might be artificial, we need something similar. Enter the Loeb Scale, also known as the Interstellar Object Screening System, or IOSS. It's a 0 to 10 classification scheme proposed by Avi Loeb to rank interstellar objects based on how anomalous they are. 0 means completely normal, definitely natural. 10 means confirmed artificial, no doubt about it. And the interesting action happens in the middle, where you're weighing unusual features against natural explanations. Think of it like the Torino scale for asteroid impacts, but instead of measuring collision risk, you're measuring the probability of artificiality. The scale reserves 8 through 10 for objects where we have strong reproducible evidence of technology. We're talking narrowband radio transmissions, engineering signatures in light curves, or direct imaging of structures that can't be explained by geology. We've never hit an 8 or above. We've never even come close. At the other end, 2I/Borisov, the second interstellar visitor, sits comfortably near 0. It looked like a comet, behaved like a comet, had a nice carbon monoxide-rich composition, consistent with formation in a cold molecular cloud around another star. Borisov was exotic because it was interstellar, but its properties were thoroughly mundane. Score, natural, move along. Then there's 1I/Oumuamua. Ah, Oumuamua, the gift that keeps on, giving astronomers headaches. Discovered in October 2017, Oumuamua was the first confirmed interstellar object, and it was immediately bizarre. Elongated, tumbling, no visible coma or tail despite passing close to the Sun. And then came the non-gravitational acceleration, a tiny but measurable deviation from a pure Keplerian orbit, as if something was gently pushing it. Comets do this all the time due to outgassing, but Oumuamua showed no signs of outgassing. No dust, no gas, just acceleration. Loeb famously suggested it could be a light sail, a thin, reflective sheet pushed by solar radiation pressure, either a piece of interstellar debris or a defunct probe. The mainstream explanation is that it was outgassing something invisible, like pure hydrogen, which wouldn't leave a visible coma but could still produce thrust. On the Loeb scale, Loeb himself scores Oumuamua at around a 7, highly anomalous, not easily explained but not confirmed artificial. The scientific community generally scores it lower, maybe a 3 or 4, unusual, deserving of attention, but probably natural with some exotic twist we haven't fully understood yet. So where does 3i Atlas fall? Loeb describes it as high middle. Not as extreme as Oumuamua, but significantly weirder than Borisov. Let's break down what scores on the Loeb scale for this object. Geometry. The low inclination, approximately 5 degrees off the ecliptic, is unusual for an interstellar arrival. Not impossible, but statistically uncommon. That ticks up the score. Timing. The solar conjunction coinciding with perihelion passage, creating a blind spot for Earth-based observations right when the object is most active. Coincidence? Maybe. Or maybe convenience. Another tick. Chemistry. The carbon dioxide to water ratio of 8:1 is extreme. It's within the realm of natural comet diversity, but it's on the far edge. The enormous CO2 coma detected by Spherex adds weight. This is significant. Nickel without iron. The metal emission pattern is hard to explain with standard cometry models. Organometallic pathways exist, but they're exotic. The delayed appearance of iron, if iron never shows up in strength, would be very hard to square with natural heating. Optical asymmetries. Loeb's interpretation of a forward glow is contested, but if confirmed, it would suggest directed emission rather than passive scattering. That would be a big deal. Right now, the score sits somewhere around a 5 or 6. Interesting. Worth watching, not conclusive. But here's the thing about the Loeb scale. It's dynamic. The score can change with new data. If 3i Atlas re-emerges from solar conjunction and shows a non-gravitational acceleration that can't be explained by outgassing, that bumps the score up. If JWST detects narrow band emissions in specific frequencies, that's a huge bump. If follow-up observations reveal periodic brightness variations that look engineered, regular, geometric, not random, then you're pushing into the high 7s or 8s. Conversely, if the object's post-conjunction orbit fits perfectly with gravity alone, if water vapour increases as it heats up and the carbon dioxide ratio normalises, if iron emission lines appear right on schedule, then the score drops, maybe down to a 3. Weird, but natural. What would push it to a 9 or 10? That's the smoking gun territory. You'd need communication. You'd need unambiguous evidence of structure. You'd need something that cannot, under any physical scenario we understand, be a natural object. For example, imagine 3i Atlas starts emitting a repeating radio signal. Not random noise, not naturally occurring master emission, a pattern, a code. That's a 9, maybe a 10, depending on the content of the signal. Or imagine high-resolution imaging, say, from a spacecraft intercept mission like the proposed Juno flyby that resolves angular features, flat surfaces or modular structures. That's a 10. Game over. We're not alone, but we're not there, not even close. And it's crucial to understand what NASA and ESA are saying publicly, because there's been a lot of media noise around this object. NASA has explicitly stated that 3i Atlas is a natural comet pending evidence to the contrary. The agency has also rebutted media overhyping of alien probe claims, emphasising that current observations are consistent with known cometary behaviour. That's the conservative evidence-based position, and it's the right default. Extraordinary claims require extraordinary evidence. The burden of proof is on the "this is technology" hypothesis, not the "this is a comet" hypothesis. Comets are common. Alien spacecraft visiting our solar system are, as far as we know, non-existent. So why are we even talking about this? Because the evidence is accumulating in a direction that makes the natural explanation less comfortable over time. Not impossible, just less satisfying. And because the solar conjunction is about to cut off our view, and when we can see it again, we'll have a much clearer picture. Here's how you, as an engaged observer, can watch the score evolve. Track these signals, astrometry. Does the object's position match predictions based purely on gravity, or are there residuals, tiny deviations that suggest thrust? Spectroscopy. Does the volatile composition change as expected with solar heating, or does it stay anomalous? Metal lines. Does iron finally show up, or does the nickel dominance persist? Light curve. Does the brightness vary in predictable ways due to rotation and dust production, or are there irregular spikes that suggest something else? Photometry at re-emergence. Any sudden brightness changes when it reappears from behind the sun. These are the data points that will move the needle, and they're all testable. That's the beauty of science. You make predictions, you take measurements, and reality tells you if you're right or wrong. Right. Now 3i Atlas sits in the uncomfortable middle of the lobe scale, anomalous enough to warrant attention, not anomalous enough to overturn the natural hypothesis. But with a critical observational gap coming, and the possibility of data from Mars orbiters and eventually a Jupiter flyby, the story is far from over. One more thing to address before we move on: selection bias. Skeptics rightly point out that we notice weird things because they're weird. If 10,000 interstellar objects pass through the solar system and 9,999 are boring, we're going to obsess over the one oddball. That doesn't mean the oddball is artificial, it might just mean it's the natural outlier we happen to catch. Fair point. But here's the counter-argument. We've only detected 3 interstellar objects. Ever. 3. And 2 of them, Oumuamua and 3i Atlas, are in the weird category. That's not a statistical sample. That's not even a trend. It's a curiosity. But it's a curiosity that demands we pay attention. The lobe scale isn't a verdict. It's a framework, a way of organising our uncertainty. And right now, 3i Atlas is uncertain enough to keep us watching. But how improbable is coincidence, really? If you wanted to calculate the odds that a random interstellar object would arrive with this specific geometry, this specific timing, this specific chemistry, could you? Let's try. Part 4. The mathematical improbability of coincidence. Let me ask you a question. If you stood in the middle of a football field and someone on the moon threw a dart, and that dart landed within 10 feet of you, would you assume it was random, or would you start asking questions? That's the essence of what we're dealing with when we try to quantify the improbability of 3i Atlas's trajectory. It's a thought experiment in cosmic odds, and while the math gets complicated fast, the basic idea is simple. How often would a random interstellar object hit the specific set of conditions we're seeing? First, let's talk about the ecliptic alignment. The ecliptic plane is the flat disk where Earth and the major planets orbit. It's a thin slice through 3-dimensional space. If you imagine interstellar objects approaching from truly random directions, from all possible angles in the celestial sphere, the probability of one arriving within 5 degrees of the ecliptic is approximately 1 in 36. That's just basic spherical geometry. Not crazy rare, but not common either. You'd expect about 1 in every 36 interstellar objects to have a low inclination like this. But we've only detected 3 total, so our sample size is too small to say if 3i Atlas is genuinely unusual or just the 1 in 36 we happen to catch. Now add the timing. Perihelion occurs on October 29th through 30th, 2025 at the start of solar conjunction. That's the window when Earth loses line of sight to the object for several weeks. Is that coincidental? Well, solar conjunctions happen predictably based on geometry. Any object passing close to the Sun will at some point be on the opposite side from Earth. The question is whether the most active period of the comet's outgassing happens to align with that blind spot. For most comets, peak activity happens near perihelion, when solar heating is strongest. So yes, perihelion and conjunction overlapping is somewhat expected. But the fact that it's a prolonged conjunction, spanning weeks, does feel convenient. Let's think about it differently. If you were designing a mission to study the inner solar system while minimizing detection from Earth, what would your trajectory look like? You'd probably want low inclination, so you're moving through the plane where planets and interesting stuff are. A perihelion passage that puts you on the far side of the Sun from Earth at peak activity. Sequential close approaches to multiple planets for observational opportunities. 3i Atlas checks all 3 boxes. Mars on October 3rd, perihelion during conjunction late October, Jupiter on March 16th, 2026. It's a tour. Now, here's where the statistical argument gets murky. We don't have good priors. We don't know how many interstellar objects pass through the solar system undetected. Estimates based on Oumuamua's discovery suggest there might be one detectable interstellar object within one astronomical unit of the Sun at any given time, implying a population of thousands passing through the wider solar system annually. But most are too faint or too far away to spot. If interstellar objects are common, then rare configurations become less surprising. Roll the dice enough times and eventually you'll get snake eyes. But if interstellar objects are exceedingly rare, then even one with unusual properties demands explanation. Let me give you a Monte Carlo thought experiment, even though I'm not going to run the actual simulation here. Imagine you generate 10,000 random interstellar trajectories, random inclinations, random entry velocities, random orientations. You then ask, how many of those trajectories pass within 5 degrees of the ecliptic, achieve perihelion during Earth-solar conjunction, and come within reasonable distance of both Mars and Jupiter within a 6-month span? My guess, based on rough geometric probability, is somewhere between 0.1% and 1%. Maybe 1 in 100 to 1 in 1,000 random interstellar objects would satisfy all those conditions. That sounds rare, but again, if thousands of interstellar objects pass through annually, you'd expect to see a few like this per century. The problem is we're not seeing a few per century, we're seeing one, and it's happening now, and it's also got weird chemistry and unusual metal emissions layered on top of the weird geometry. Let's compare to the other two, interstellar objects. Oumuamua had an orbital inclination of about 122 degrees, highly tilted relative to the ecliptic. It came in steep, passed through, and left steep. Its trajectory was definitely not plane aligned, but it did have that mysterious non-gravitational acceleration, which is its own can of worms. 2I/Borisov had an inclination of about 44 degrees, also tilted, not particularly plane aligned, and Borisov was chemically normal. Carbon monoxide, water, dust, all the things you'd expect from a comet born around another star. So we don't have 3 similar cases, we have 3 very different cases. That makes it hard to claim a pattern. You can't argue that all 3 interstellar objects are weird in the same way, because they're not. Oumuamua was weird in one way, Borisov was normal, and 3I Atlas is weird in a completely different way. Which brings us to the question of natural scenarios. How do you get a low-inclination interstellar object naturally? One possibility, it was ejected from a planetary system during formation, and planetary systems tend to be flat disks. If the ejection happened in the plane of that distant system, and if that plane happened to be aligned with our ecliptic by chance, then low inclination is explained. The odds of such an alignment aren't great, but they're not zero. Another possibility, the object's trajectory was gravitationally perturbed by a close encounter with another star during its interstellar journey. Stars pass relatively close to each other in galactic terms, and a near miss could bend an interstellar object's path. If that encounter happened at just the right angle, it could rotate the trajectory into our ecliptic plane. Both scenarios are plausible, both are natural. Both require coincidences, but coincidences happen. The alternative hypothesis is targeting. If 3I Atlas is an artificial probe, its trajectory would have been deliberately chosen to optimize solar system exploration. Low inclination to stay in the planetary plane, timed conjunctions to avoid observation, sequential flybys of Mars and Jupiter for data collection. From a mission design standpoint, this is exactly what you'd plan. But here's the intellectual honesty part. We cannot, with current data, distinguish between natural object with lucky geometry and designed object with optimal geometry. The math doesn't give us enough leverage. The trajectories are consistent with both hypotheses. What would firm up the odds calculation? More data. Specifically, more interstellar objects. If the Vera C. Rubin Observatory's legacy survey of space and time comes online and starts detecting dozens or hundreds of interstellar objects over the next decade, we'll finally have a statistical baseline. We'll know what typical looks like. We'll know how often low-inclination arrivals happen, and then we can say with confidence whether 3I Atlas is genuinely anomalous or just the first one we noticed. Until then, we're stuck with small number statistics and unsatisfying probabilities. But I'll leave you with this thought. Coincidence is emotionally uncomfortable. When something rare happens at a convenient time in a convenient way, our brains scream not random, But rarity isn't evidence. Improbability isn't proof. Things that are 1 in 1,000 do happen, and they happen to someone somewhere at some time. The question is, are we that someone? Did we just happen to be the civilization that spotted the weird 1 in 1,000 interstellar object? Or is the 1 in 1,000 probability itself wrong, and we're looking at something far more deliberate? The math can't tell us yet, but the clock can, because in less than a month 3i Atlas will disappear behind the sun, and when it's gone, we're blind. If a course change is going to happen, if any evidence of artificiality is going to manifest, that blackout window is when it matters most. The silence before the sun. That's next. Part 5. The silence before the sun. There's a particular kind of suspense that comes from knowing you're about to lose sight of something important. It's the feeling you get when a car disappears around a corner just as you notice its erratic driving. You can't follow, you can't track, you can only wait and hope that when it reappears, everything is still normal. 3i Atlas is about to disappear around a cosmic corner, and it's going to stay gone for weeks. Let me walk you through the timeline and the geometry, because this is where the stakes get real. Perihelion, closest approach to the Sun, happens on October 29th and 30th, 2025. That's when the comet is at about 0.96 astronomical units from the Sun, well inside Earth's orbit, being blasted by intense solar radiation. For a natural comet, this is peak activity time, ice sublimating, dust erupting, the coma and tail at maximum brightness. It's also when solar conjunction begins. From Earth's perspective, 3i Atlas passes behind the Sun, not literally behind, as in eclipsed, but close enough in angular separation that the Sun's glare drowns out any chance of observing it. Ground-based telescopes can't point that close to the Sun without risking damage or getting useless data. Hubble space, T. Continu telescope has strict sun avoidance angles. It can't observe anything within about 50 degrees of the Sun, or it risks frying its sensitive instruments. Even JWST, sitting out at the L2 Lagrange point, has pointing constraints that make observing objects near the Sun geometrically difficult or impossible. The blackout starts in late October 2025 and extends into late November. That's roughly 4 weeks. 4 weeks where the most active, most interesting interstellar object we've ever tracked simply vanishes from our view. The European Space Agency has confirmed this. Timeline. Their official statements note that the object will reappear in late November, and they're setting expectations appropriately. During conjunction, observations will be extremely limited. Mars Express and the Trace Gas Orbiter may attempt distant monitoring around October 3rd, but those spacecraft aren't optimized for this kind of work, and the signal-to-noise ratio will be poor. Now, let's talk about why this blackout window is tactically perfect. If, and this is a big if, something artificial is at play. Imagine you're piloting a spacecraft through an alien star system. You want to study the inner planets, take measurements, maybe deploy instruments or probes. But you also want to minimize the chance of being detected or tracked by any observers on those planets. What do? You time your closest approach to coincide with a period when the dominant intelligent species on the third planet cannot observe you. You use their star as a shield. You make your move during the solar eclipse of their awareness. Avi Loeb, in multiple interviews and essays, has called this the perfect time to maneuver. If 3i Atlas were going to change its trajectory, fire a thruster, adjust its course, deploy secondary objects, the conjunction window is when you'd do it. By the time Earth-based observatories regain line of sight in late November, the evidence of manoeuvring would be diluted. The object would be on a new trajectory, but without continuous tracking. Astronomers would have a harder time proving exactly when and how the change occurred. Now let me be clear, this is speculation. This is a what-if scenario. There is no evidence that 3i Atlas has manoeuvring capability. There is no evidence it's going to do anything during conjunction, except continue on its predicted orbital path, outgassing naturally as it heats up and cools down. But the timing does make you think. Can we observe it at all during the blackout? The short answer is barely, and indirectly at best. Solar coronagraphs, instruments designed to study the Sun's corona, can sometimes detect bright comets passing very close to the Sun. The Solar and Heliospheric Observatory, SOHO, has discovered thousands of sun-grazing comets this way. But 3i Atlas isn't passing close enough to the solar limb for those instruments to catch it. It's too far out and likely too faint. So coronagraphs are probably a dead end. Radio occultation. When an object passes behind the sun, radio signals from spacecraft can be bent or disrupted by the sun's plasma and magnetic field. In theory, you could detect an object's presence by the way it perturbs those signals. But 3i Atlas isn't a radio emitter, and it's not large enough to cause detectable gravitational lensing. So radio occultation is also unlikely to help. There are some very speculative monitoring options. Cosmic ray detectors and meteoroid counters on spacecraft throughout the solar system could, in principle, register unusual particle fluxes if the comet were shedding material in unexpected ways. But those instruments aren't designed for targeted comet observation, and the data would be noisy and hard to interpret. The reality is this: during conjunction, we're effectively blind. What we can still do, and what makes the post-conjunction observations so critical, is prepare. Astronomers are planning to scrutinise 3i Atlas the moment it reappears, and they know exactly what to look for. Here's the checklist. Light curve continuity. Did the brightness evolve as expected based on solar heating models? Or were there sudden jumps or drops that suggest structural changes or material release? Spectroscopy. Is the carbon dioxide to water ratio still 8:1, or has it shifted? Does iron emission finally appear alongside nickel, indicating natural thermal progression? Position residuals. Does the object's observed position match predictions based on a purely gravitational trajectory, or are there discrepancies that suggest acceleration? Morphology. Has the tail or coma structure changed in unexpected ways? Any new jets, asymmetries, or features that weren't present before conjunction? Polarization. Follow up polarimetry measurements to see if the extreme negative branch seen earlier persists or evolves. These are all testable, quantifiable metrics, and they'll be available within days of the object re-emerging from behind the sun. But here's what keeps people like Avi Loeb, and frankly, a growing number of professional astronomers, up at night. If something does happen during the blackout, we'll only find out after the fact. We'll see the evidence, but we won't have witnessed the event itself. It's like arriving at a crime scene and trying to reconstruct what happened based on forensics. You can make strong inferences, but you don't have the video footage. The timing with Mars and Jupiter adds another layer of intrigue. On October 3rd, 2025, just days from now, 3i Atlas passes relatively close to Mars, about 30 million kilometres away. That's close enough that the European Space Agency is planning to aim Mars Express and the Trace Gas Orbiter at it. These aren't purpose-built comet observatories, and the viewing geometry isn't great, but they'll try. Why does Mars matter? Because it's a different vantage point. If the comet is doing something directional, venting asymmetrically, emitting signals, deploying objects, observers at Mars might see something Earth-based telescopes can't. It's triangulation. Multiple perspectives reduce ambiguity. Then, on March 16th, 2026, the object passes within 0.358 astronomical units of Jupiter, roughly 33 million miles. That's close enough for very good observations, assuming we still have tracking by then. Jupiter's orbital position at that time will offer yet another distinct vantage point, and if NASA's Juno spacecraft manages to pull off an intercept, we'd have in situ measurements. So the sequence is Mars flyby on October 3rd, solar conjunction and perihelion late October through November, re-emergence late November, Jupiter flyby in March 2026. It's a choreographed set of opportunities if you're looking for them. Let me address the fear factor, because I know what some of you are thinking. What if it does something bad during the blackout? What if it releases something dangerous? NASA and ESA have been unequivocal. 3i Atlas poses no threat to Earth. The geometry doesn't allow for an impact. Even if it broke apart into thousands of pieces during perihelion, those pieces would not intercept Earth's orbit. The closest approach distance is 1.8 astronomical units, over 160 million miles. For comparison, the Moon is only 240,000 miles away. There's no impact risk. Could it release probes that change course and head toward Earth? In principle, yes, but you'd need a lot of delta V, change in velocity, to redirect something from an interstellar trajectory onto an Earth intercept path. We're talking kilometers per second of thrust. That's rocket engine level propulsion, and we detect the thermal signature of such a burn even during conjunction if it were pointed toward us. The realistic worst case scenario isn't danger, it's ambiguity. It's the possibility that something odd happens during the blackout, and we're left arguing about whether it was natural outgassing or something else, without the continuous data to settle the debate definitively. And that's the thing about solar conjunctions. They're not just observational inconveniences, they're gaps in the historical record. We can interpolate across them, but we can't rewind and watch what actually happened. Loeb has repeatedly emphasised this point in his essays and interviews. He calls it the perfect window, not because he's asserting something will happen, but because if you were designing a mission and wanted operational security, this is the window you'd choose. It's not proof of intent, it's an acknowledgement of opportunity. So what happens next? In less than 4 weeks, 3i Atlas crosses behind the Sun and goes silent. We wait. We monitor what little we can from Mars orbiters. We prepare our instruments for reacquisition, and then, in late November, we look. If the object reappears exactly where we expect, with a light curve and spectrum consistent with natural cometary evolution, then the score on the Loeb scale probably drops. Coincidence remains the best explanation, and we chalk it up to an unusually weird but ultimately natural comet from the space between stars. But if there are surprises, if the position is off, if the chemistry has shifted in unexplained ways, if new features appear, then the questions deepen, and the hypothesis that we're not looking at a comet, but at something else, gains weight. The silence before the Sun is almost here, and when the silence breaks, we'll know more. Maybe not everything, but more. Which brings us to the idea that's been hovering at the edge of this entire discussion, the hypothesis that makes some astronomers roll their eyes and others lean in with uncomfortable curiosity. What if 3i Atlas isn't a single object? What if it's a carrier? Part 6. The Mothership Hypothesis Revisited. Let me be very clear up front. What I'm about to describe is speculation. This is not established science. This is a hypothesis, one that Avi Loeb has explored in the context of interstellar objects, and one that has gained renewed attention with 3i Atlas. But it is not proven. It's a framework for thinking about what signs we'd look for if an interstellar visitor were more than just a rock or an ice ball, the Mothership Hypothesis. The idea goes like this. What if some interstellar objects aren't monolithic, single chunks of matter, but are instead carriers? Vessels designed to traverse the vast distances between stars, possibly carrying smaller probes or instruments that can be deployed upon arrival at a target star system. Think of it as the cosmic equivalent of a research ship launching survey drones. Loeb first floated versions of this idea in the wake of Oumuamua. He suggested that Oumuamua itself might have been a defunct light sail, or that it could have deployed smaller probes that we didn't detect. The scientific community was, let's say, skeptical. But the hypothesis was never about Oumuamua specifically. It was about establishing a search framework. If interstellar probes exist, what would we look for? Now, with 3i Atlas, some of those same questions are resurfacing. Not because we have proof, but because the object's behaviour invites the question. If 3i Atlas were a carrier, what signs might we expect? Short-lived micro-brightness spikes. If the object were releasing smaller secondary objects, probes, instruments, whatever, those releases might cause brief, localised brightening as surfaces are exposed or materials vent. These spikes would be small, possibly lasting only minutes or hours, and they'd be incredibly hard to distinguish from normal cometary jet activity, unless you were specifically looking for them with high-cadence photometry, unusual radar or specular reflections. Natural comets are rough, porous, covered in dust and irregular ice. Radar signals bounce off them in diffuse scattered ways. But if part of 3i Atlas had smooth metallic surfaces, unlikely for a comet, you might see unexpectedly strong specular radar returns. We haven't done radar observations of this object yet, to my knowledge, but it's something that could be attempted during re-emergence. Post-conjunction debris trains. If probes were deployed during the solar blackout, they might form a debris train, a linear structure of smaller objects trailing the main body. These would show up as faint secondary sources in wide-field imaging. Again, natural comets can fragment and produce debris, so distinguishing between a natural breakup and a deliberate deployment would be tricky. Now, let's revisit the headlights claim in this context. Loeb's observation of a forward sunward glow could be interpreted speculatively as active thermal management. If 3i Atlas were artificial, and using the sun's heat to power systems, you'd expect a hot sunward face. And if that face were venting carbon dioxide to control temperature, acting as a radiator, you'd see exactly the kind of bright directional emission Loeb describes. Here's where the 8:1 carbon dioxide to water ratio becomes interesting. Carbon dioxide sublimates at lower temperatures than water ice. If you were designing a passive thermal management system for a spacecraft approaching a star, you'd want a volatile that vents easily and carries away heat without requiring active pumps or compressors. CO2 fits that bill. Water, by contrast, is stickier, harder to manage, and freezes in inconvenient ways. So a spacecraft venting carbon dioxide as a coolant would look, chemically, a lot like what JWST and SphereX observed. Emphasis on would look like. This is not proof. This is pattern matching. Now let's talk about the nickel. The detection of strong nickel emission without corresponding iron is one of the most chemically peculiar aspects of 3I Atlas. Natural explanations exist: organometallic compounds, photon-stimulated desorption, preferential release pathways, but they're all exotic and not fully fleshed out yet. What if the nickel is process effluent? What if it's an incidental byproduct of whatever systems are operating inside the object? Nickel-bearing compounds, especially carbonyls like nickel tetracarbonyl, are used in certain industrial processes. They're also incredibly toxic and volatile, which makes them unlikely spacecraft materials, but who knows what engineering solutions an advanced civilization might develop. If internal heat sources or chemical reactions were breaking down nickel-bearing materials, you'd release nickel atoms into the coma. And if those materials didn't include comparable amounts of iron, or if iron was sequestered in some other form, you'd get the nickel without iron signature we're seeing. Again, this is speculative, but it's not physically impossible. Why would probe dispersal favour the conjunction window? Because that's when you're least likely to be observed. If you're deploying secondary objects, whether they're passive sensors falling toward the inner planets, or active probes changing course, you want to do it when ground-based tracking is minimised. The solar conjunction provides that window. Now let's pump the brakes and consider the counter-arguments because they're strong. First, dust jets and phase effects explain a lot. Comets are messy, asymmetric objects. Localised venting from active regions on the nucleus can create forward-facing jets that look directional. The interplay of sunlight, dust scattering, and observing geometry can produce all kinds of optical illusions. Before you invoke spacecraft, you need to rule out the mundane explanations. Second, carbon dioxide-rich comets exist. Comet C/2016 R2, discovered in 2016, is a famous outlier. It had an unusually high carbon monoxide and carbon dioxide abundance, likely because it formed in a particularly cold region of its birth system. Weird chemistry happens naturally. It's rare, but it's not impossible. Third, fragmenting comets are common. If 3I Atlas breaks apart during perihelion, a natural process caused by thermal stress and tidal forces, it will produce debris. That debris will look like a swarm. It won't be probes. It'll be chunks of ice and rock. And distinguishing between natural fragmentation and deliberate deployment from Earth-based observations alone is nearly impossible without extremely detailed tracking. So what would constitute observable consequences if the carrier hypothesis were true? The most definitive would be anomalous accelerations after the conjunction. If 3I Atlas reappears on a trajectory that doesn't match a purely gravitational orbit, if there are position residuals that can't be explained by outgassing or radiation pressure, that's a smoking gun. It means thrust. It means control. Another possibility is transient meteor entries. If small probes were deployed and some of them entered Earth's atmosphere, they'd produce meteor events. But here's where we have to be very careful not to fall into sensationalism. The Earth is constantly bombarded by natural meteoroids, tens of thousands per day. A handful of unusual meteor reports during or after the conjunction would not, by themselves, prove anything. You'd need coordinated observations from multiple meteor camera networks, with trajectory reconstructions that clearly link the meteors back to 3I Atlas. That's doable, but it requires discipline. Third, radar follow-ups. If astronomers can get radar time on facilities like Arecibo... Oh wait, Arecibo collapsed. Okay, if they can get radar time on Goldstone or the upgraded Arecibo replacement, whenever that comes online they could ping 3I Atlas and look for unusual returns. Specular reflections, geometric shapes, anything that doesn't look like a random pile of rubble. What data do we actually need to test the carrier hypothesis? high-cadence photometry during re-emergence. You need continuous brightness measurements at intervals of minutes, not hours, to catch transient events. Wide-field meteor network monitoring. Systems like the All-Sky Meteor Orbit System, or AMOS, which track meteor trajectories, should be watching during and after the conjunction for anything unusual. Astrometry, with the highest possible precision. Use Gaia. Use ground-based telescopes. Use JWST if possible. Get the position measurements accurate to milliarc seconds and compare them to predictions. And here's the risk we absolutely must acknowledge: pareidolia. The human brain is wired to see patterns, agency and purpose even in random data. We see faces in clouds. We hear messages in static. When we're primed to look for probes, we'll find probes, even if they're just ice chunks. The history of astronomy is full of false alarms. Percival Lowell saw canals on Mars because he expected to see them. Early SETI researchers got excited about signals that turned out to be terrestrial interference. The WOW signal remains unexplained, but it was never repeated. We have to guard against fooling ourselves. So how do you avoid pareidolia? You pre-register predictions. You specify in advance what measurements would confirm or falsify the hypothesis. You don't retrofit explanations after the fact. You let the data lead, not your expectations. The mothership hypothesis is exactly that. A hypothesis. It's testable. It makes predictions. And if those predictions fail, it should be discarded. But here's the uncomfortable part. If it's not discarded, if the post-conjunction data show features consistent with deployment or manoeuvring, then we're in uncharted territory. Because at that point, we're not just talking about a weird comet anymore. We're talking about something that chose to come here. And that brings us to a historical question. Has hiding behind the sun ever been done before? Not by interstellar visitors, but by us. Have human missions used solar conjunctions for operational advantage? Turns out yes, and the playbook is well established. Part 7. Behind the Sun Tactics in Aerospace History. Solar conjunction isn't just an astronomical curiosity. It's an operational reality for anyone trying to communicate with or observe objects near the Sun. And throughout the history of space exploration, mission planners have had to work around it, or in some cases, exploit it. Let me give you a quick tour of how conjunctions have played out in human spaceflight and astronomy. Mars missions are the classic example. Every 26 months, Earth and Mars align such that Mars passes behind the Sun from our perspective. During those conjunction windows, which last about 2 weeks, radio communication with Mars rovers, orbiters and landers becomes unreliable or impossible. The Sun's corona, a roiling soup of charged particles and magnetic fields, scatters and distorts radio signals. You can sometimes push data through, but it's corrupted, slow and risky. So NASA and ESA have a standard protocol. During Mars solar conjunctions, rovers go into safe mode. They stop driving. They run minimal operations. Orbiters continue their observations but store data on board instead of transmitting it back to Earth. Then, once the conjunction ends and clean communication is restored, the data gets downloaded and normal operations resume. This is a forced blind spot. Mission controllers hate it because they lose real-time awareness, but it's unavoidable given the geometry. Apollo missions faced a similar challenge, though not with the Sun. During lunar farside passes, the Apollo spacecraft lost all radio contact with Earth. The Moon itself blocked the signals. For those periods, sometimes half an hour or more, astronauts were completely on their own. Mission Control couldn't see their telemetry, couldn't talk to them, couldn't help if something went wrong. It was radio silence. And it was during one of those farside passes on Apollo 8 that Frank Borman, Jim Lovell and Bill Anders fired their engine to leave lunar orbit and head home. Earth didn't know if the burn had succeeded until the spacecraft reappeared from behind the Moon. The blackout added a layer of suspense to an already tense operation. Now let's talk about the classified side of things, because this is where it gets interesting. Military and intelligence satellites operate with geometry in mind. If you're running a reconnaissance satellite, you care deeply about who can see you and when. Certain orbits, geosynchronous orbits for example, keep satellites over specific regions of Earth, making them predictable targets for ground-based observation. If a rival nation has optical or radar tracking, they can monitor your spacecraft's activity. But if you time maneuvers or deployments to occur when your adversary's ground stations don't have line of sight, say during local daylight, when optical telescopes can't observe, or when the satellite passes over an ocean with no nearby tracking assets, you reduce detection risk. The sun offers an even better shield. If you're operating a space asset and you want to minimise scrutiny from ground-based observers, you can use solar conjunction as cover. Position your spacecraft such that, from the perspective of watchers on Earth, it's close enough to the sun's glare that optical telescopes can't see it. This isn't speculation, it's basic orbital mechanics and operational security. Militaries think about these things, geometry as a weapon and a shield. Now, does that mean 3i Atlas is using this tactic? No. It means that if control existed, if the object were artificial and deliberately navigating, it would be operationally smart to manoeuvre during conjunction. The tactic has precedent. Let's think about feasibility. Could an object actually hide its manoeuvres during a solar conjunction? Yes and no. Any large delta V burn, any significant change in velocity produces heat. Rocket engines are hot. Thruster plumes glow. If 3i Atlas fired a chemical rocket during conjunction, spacecraft with infrared sensors elsewhere in the solar system might detect the thermal flash. NASA has infrared space telescopes. The Department of Defense has classified early warning satellites designed to spot missile launches, which detect infrared signatures. If something big happened, someone might see it, even if ground telescopes couldn't. But a small, efficient burn, a cold gas thruster using nitrogen or carbon dioxide venting, that could be subtle, especially if it were done in a direction pointed away from Earth and other major observing assets. The other constraint is astrometry. Even if you can't watch an object during conjunction, you can check its position before and after. If 3i Atlas reappears in late November, and its position doesn't match the predicted gravitational trajectory, that's evidence of acceleration. The timing would be uncertain. You'd know it happened during the gap, but not exactly when, but the fact of manoeuvring would be clear. So, could a manoeuvre be hidden? Partially. The thermal signature might escape notice, but the gravitational fingerprint would remain. Orbits don't lie. What wouldn't be hidden is the physics. Gravity is relentless. If you change an object's trajectory, you leave an imprint in the ephemeris, the table of predicted positions. Post-conjunction astrometry will either match the predictions or it won't. There's no faking that. Which brings us to an important point. Even if something did manoeuvre during the blackout, we'd still have evidence afterward. We wouldn't have the video footage, but we'd have the forensics. And in science, forensics are often enough. The behind-the-sun tactic is real. It's been used. It's understood. But it's not magic. It buys you operational secrecy in the moment, but not immunity from detection afterward. In 3i Atlas's case, the chemistry might be a bigger tell than the trajectory. Because if the object is venting carbon dioxide as part of some thermal or propulsion system, that chemistry persists. It's not something you can hide. It's baked into the spectrum. Which brings us full circle to the carbon dioxide mystery. Why is this thing venting so much CO2? Why is the ratio 8:1 over water? And what does that tell us about what 3i Atlas actually is? Let's dig into the carbon dioxide data, because this is where natural and artificial explanations collide most directly. Part 8. The carbon dioxide mystery. If you've ever tried to read a scientific paper about cometary chemistry, you know it's a slog. Absorption lines, emission bands, column densities, abundance ratios, it's dense stuff. But buried in that jargon is one of the most important clues we have about 3i Atlas. So let me translate. On August 6, 2025, the James Webb Space Telescope observed 3i Atlas using its near-infrared spectrograph, or NIRSPEC, and its mid-infrared instrument, or MIRI. These instruments measure light in the infrared part of the spectrum, where molecules like water, carbon dioxide, and carbon monoxide emit characteristic signatures. The results were released on August 25th, and they were strange. JWST detected strong emission from carbon dioxide at 4.3 micrometers, a wavelength where CO2 molecules vibrate and glow when excited by sunlight. That's normal. Comets often have carbon dioxide. What's not normal is how much of it there was compared to water. The measured ratio of carbon dioxide to water was 8.0, plus or minus 1.0. That means for every molecule of water vapour in the coma, there were 8 molecules of carbon dioxide. In plain English, this comet is venting 8 times more CO2 than H2O. Why is that weird? because water is supposed to be the dominant ice in comets. Comets are dirty snowballs, remember? The snowball is water ice. Other volatiles, carbon monoxide, carbon dioxide, methane, ammonia, are present, but usually as trace components or secondary ices mixed in with the dominant water. Finding a comet where carbon dioxide is the main event is like finding a snowman made of dry ice. It can happen. But it's not typical. Let me give you the numbers for context. In most comets, the CO2 to H2O ratio is well below 1, a ratio of 0.1, meaning 10 times more water than carbon dioxide is common. A ratio of 0.5 is on the high side. A ratio of 2 or 3 would be unusual. A ratio of 8 is basically off the charts. SPHEREX, the space telescope designed to map infrared emissions across the sky, also observed 3I Atlas and found something equally striking. The carbon dioxide coma extends at least 348,000 kilometres from the nucleus. That's enormous. For comparison, the distance from the Earth to the Moon is about 384,000 kilometres. So this comet is wrapped in a bubble of carbon dioxide that's nearly as wide as the Earth-Moon system. And SPHEREX did not detect comparable emissions from water or carbon monoxide at the same time, meaning the carbon dioxide dominance isn't just a quirk of one observation or one instrument, it's consistent. So, what explains this? Let's start with the natural hypotheses, because those are where we should always start. Hypothesis 1. Formation location. Comets form in the outer regions of star systems, where temperatures are cold enough for volatiles to condense into ice. Different molecules freeze at different temperatures. Water ice condenses at around 150 to 200 Kelvin. Carbon dioxide ice condenses at a slightly lower temperature, around 60 to 80 Kelvin. If 3I Atlas formed in a particularly cold region of its birth system, far from the star, perhaps in a dense molecular cloud, it might have accumulated more carbon dioxide relative to water. This is plausible. We know that different regions of protoplanetary disks have different chemical compositions. The snow line in our own solar system, where water ice becomes stable, is around 2.7 astronomical units from the Sun. Further out, you get carbon dioxide, methane, ammonia ices. A comet that formed beyond the carbon dioxide line would naturally be CO2-rich. Hypothesis 2. Radiation processing. Interstellar space is not empty. It's filled with cosmic rays, ultraviolet starlight, and high-energy particles. Over millions of years, these can chemically alter the surface of a comet, breaking apart water molecules and creating a radiation-processed crust. If the surface layers of 3I Atlas were depleted in water, but retained carbon dioxide, you'd see a high CO2 ratio in the early outgassing. As the comet heats up closer to the Sun, this crust could erode or sublimate away, exposing fresher ice underneath. In that case, you'd expect the carbon dioxide to water ratio to decrease over time as water-rich layers are exposed. This is testable. If post-conjunction observations show water increasing and the ratio dropping, that supports the radiation processing hypothesis. Hypothesis 3. Grain-driven release. Sometimes water ice in comets is locked up in dust grains or clathrate structures, cage-like ice formations where water molecules trap other volatiles. If water is sequestered in this way, it sublimates more slowly than free carbon dioxide ice. Early in the comet's approach, you'd see lots of CO2 and not much H2O. Later, as temperatures rise and grains break down, water release would catch up. Again, this predicts a changing ratio. If the carbon dioxide dominance persists, even as the comet gets closer to the Sun and hotter, that's harder to explain with grain-driven models. All three of these hypotheses are scientifically sound. They're consistent with known physics and chemistry. They don't require invoking anything exotic, but they do require specific conditions, cold formation environments, prolonged radiation exposure, or unusual grain structures that are themselves somewhat rare. Now let's talk about what JWST actually mapped, because the details matter. The observations covered multiple wavelengths. Dust emission at 1.2 micrometers, carbon dioxide at 4.3 micrometers, water at 2.7 micrometers, carbon monoxide at 4.7 micrometers. They also detected carbonyl sulfide, OCS, and water ice grains. So it's not that water is absent, it's just overwhelmed by carbon dioxide. The coma has water, it just has way more CO2. The JWST team, in their preliminary reports, emphasised that this doesn't prove anything artificial. They're careful to note that extreme volatile ratios, while unusual, fall within the range of natural cometary diversity. Their job is to measure and report, not to speculate about alien spacecraft. But here's where the speculation enters, and I want to be clear. This is a what-if thought experiment, not a scientific claim. If 3I Atlas were artificial, if it were a spacecraft or probe, carbon dioxide makes a lot of sense as a working fluid. In spacecraft thermal management, you need a way to dump heat. In the vacuum of space, you can't use conduction or convection, there's no air. You have to use radiation, which is slow, or you have to vent a fluid that carries heat away with it. Carbon dioxide is an excellent choice for this. It's stable, non-corrosive, sublimates at manageable temperatures, and has good thermodynamic properties. In fact, carbon dioxide is used in some terrestrial refrigeration systems for exactly these reasons. If a spacecraft were using the sun's heat to power onboard systems, maybe through thermal radioisotope generators, or photovoltaic panels, or some other energy conversion method, it would generate waste heat. Venting carbon dioxide could be a way to shed that heat passively. And the closer the spacecraft got to the sun, the more heat it would need to dump, which means more CO2 venting. Water, by contrast, is a pain. It freezes at inconvenient temperatures. It's corrosive. It's heavy. If you're designing a spacecraft thermal system, you'd probably avoid water as your primary working fluid. So the 8:1 ratio, from an engineering standpoint, isn't crazy for an artificial object. It's exactly what you might expect. But, and this is a huge but, it's also what you might expect from a natural comet, with unusual formation history. The chemistry alone doesn't distinguish between the hypotheses. What would help distinguish them? Time evolution. If 3I Atlas is natural, its volatile composition should change as it heats up. Water should start dominating as surface layers erode and deeper, water-rich ice sublimates. The 8:1 ratio should drop to 4:1, then 2:1, then flip entirely so water is dominant. If it's artificial, the ratio might stay roughly constant, because it's driven by engineering requirements, not thermodynamic sublimation. The spacecraft dumps heat at a rate determined by its power systems, not by the sun's heating alone. So the prediction is clear. Watch the carbon dioxide to water ratio during and after perihelion. If it changes in predictable ways, natural comet. If it doesn't, that's a problem for the natural hypothesis. What can amateurs do? Believe it or not, quite a bit. Narrowband imaging with filters tuned to specific emission lines, like the C2 SWAN bands or the OH hydroxyl line, can track the coma composition over time. Coordinated campaigns where amateur astronomers around the world take images every few hours can provide time resolution that professional observatories, with their overbooked schedules, can't match. Citizen science has a real role to play here. If you've got a backyard telescope and a decent camera, you can contribute data. Upload it to the Minor Planet Center, share it with the comet observation community. Every data t-continue point helps build the statistical picture. But let's zoom out from the chemistry for a moment and think about the bigger orbital picture, because the carbon dioxide mystery is only one piece of a larger puzzle. The trajectory itself is the other piece, and when you look at where 3I Atlas is going, the sequence of planetary encounters it's threading, you start to see something that looks a lot like a plan. Whether it's nature's plan or someone else's is the question. Part 9. Orbital chess, the Mars and Jupiter connections. There's a concept in astrodynamics called a gravity assist, or a slingshot maneuver. You've probably heard of it. Spacecraft use the gravity of planets to change speed and direction without burning fuel. Voyager did it. New Horizons did it. It's how you get to the outer solar system without carrying impossibly large fuel tanks. The trick is precision. You have to arrive at exactly the right place, at exactly the right time, with exactly the right velocity, or the assist doesn't work. It's orbital chess. Every move planned thousands of kilometers in advance. 3I Atlas isn't doing a gravity assist in the formal sense. It's not being captured by planets or gaining velocity from them, but its path does thread a sequence of close approaches that, if you were designing a reconnaissance mission, would be textbook. Let's walk through the itinerary. October 3rd, 2025. 3I Atlas passes within approximately 30 million kilometers of Mars. That's not close enough for a major gravitational interaction, but it's close enough to be interesting. The European Space Agency has confirmed that Mars Express and the Trace Gas Orbiter will attempt observations during this window. Why does Mars matter scientifically? Because it's a different vantage point. These spacecraft have spectrometers, cameras and instruments that can observe the comet's coma and tail from a perspective Earth-based telescopes can't match. The geometry is favourable for studying the antisolar tail and the sunward coma structure, exactly the regions where Loeb's headlights claim is most relevant. The ESA mission planners have tempered expectations. Mars Express and TGO weren't designed for comet observation. They're optimised for studying Mars itself, its atmosphere, surface and subsurface. Pointing them at a distant, fast-moving comet is a secondary science opportunity, not a primary objective. The signal-to-noise ratio will be marginal, and the spatial resolution won't be great. But even marginal data is better than no data. And if the comet is venting asymmetrically or showing unusual brightness patterns, the Mars orbiters might catch it. From a speculative reconnaissance standpoint, Mars is also interesting because it's a planet with an atmosphere and surface features that change over time. If you were surveying the inner solar system, you'd want close-up data on Mars, not just a flyby observation, but sustained monitoring. The October 3rd encounter offers that opportunity. Late October 2025, perihelion, 0.96 astronomical units from the Sun. This is the closest approach to the star, the moment of maximum solar heating. For a natural comet, this is when outgassing peaks. For an artificial object using solar thermal energy, this is maximum power availability, and it's also when solar conjunction begins, the blackout, the gap in our observations. We've covered this already, but it's worth emphasizing. The timing is geometrically perfect. Peak activity coincides with minimum observability from Earth. March 16th, 2026. 3i Atlas passes within 0.358 astronomical units of Jupiter. That's approximately 33 million miles. For context, Jupiter's moon Io orbits at about 0.0028 astronomical units from Jupiter. So the comet isn't diving into the Jovian system, but it's getting close enough for very good observations. And this is where things get really interesting, because Jupiter isn't just the largest planet, it's also a magnetospheric powerhouse. Jupiter generates the strongest planetary magnetic field in the solar system, extending millions of kilometers into space. That magnetosphere is filled with charged particles, plasma and radiation. When objects pass through it, they interact with that environment. Dust grains get charged, plasma tails form. If the object has any conductive properties, metal, ionized gas, whatever, Jupiter's magnetic field will affect it. From a scientific standpoint, the March 2026 Jupiter flyby is a golden opportunity for long baseline triangulation. If Juno is still operational and can observe the comet, if ground-based telescopes on Earth are watching, if JWST can get time, you'll have multiple vantage points separated by hundreds of millions of kilometers. That's stereoscopic observation on a solar system scale. You can reconstruct the three-dimensional structure of the coma, measure composition gradients, track plasma interactions, the works. From a speculative reconnaissance standpoint, Jupiter is the crown jewel of planetary flybys. If you're surveying the solar system, you absolutely want data on Jupiter. Its moons, its magnetosphere, its atmospheric dynamics. Jupiter is a physics laboratory unto itself. So the sequence is Mars, Sun, Jupiter. 3 distinct environments, 3 opportunities for observation, or, if you're entertaining the artificial hypothesis, 3 targets for data collection. Now let's reality check the gravity assist analogy, because this is where people sometimes get carried away. True gravity assists require very specific delta-v maneuvers. You have to approach a planet at a precise angle and velocity, swing around it, and depart on a new trajectory with altered speed. The velocity change comes from the planet's motion. You're stealing a tiny bit of the planet's orbital energy. But for this to work, you need to be captured by the planet's gravity well, which means coming within a few planetary radii. 3i Atlas is not doing that. Its closest approach to Mars is 30 million kilometers, about 80 times the distance from Earth to the Moon. At that distance, Mars' gravitational influence is negligible. There's no meaningful assist happening. Similarly, the Jupiter flyby at 0.358 astronomical units is close in astronomical terms, but it's still outside the orbits of the Galilean moons. Jupiter's gravity will perturb the trajectory slightly, but it won't radically change it. So no, this isn't a gravity assist tour in the mission design sense. The object is following a heliocentric orbit determined by its initial velocity and the Sun's gravity. The planetary encounters are incidental, geometric coincidences based on where the planets happen to be when the comet passes through. But here's the nuance. If you were planning a survey mission, you wouldn't necessarily need gravity assists. You just need a trajectory that provided close approaches to interesting targets, and 3i Atlas's trajectory does that. The current public ephemerids, the predicted positions published by NASA's Jet Propulsion Laboratory and the Minor Planets Center, are consistent with purely gravitational motion. There are no certified non-gravitational accelerations in the data so far, meaning as far as we can tell from astrometric measurements, the object is following a ballistic path, gravity only. But those measurements were taken before the solar conjunction. If something changes during the blackout, if there's a course correction, a delta V burn, a deployment event, we won't know until after re-emergence, and by then the ephemeris will have diverged from predictions. So what patterns should we look for post-conjunction to test whether there's any design to this trajectory? Phase curve changes. The brightness of an object as a function of the angle between the Sun, the object, and the observer is called a phase curve. Natural comets have phase curves driven by dust scattering and gas emission. If the phase curve shows unexpected features, sharp spikes, asymmetries, or changes that don't match cometry models, that could indicate structural complexity or active surfaces. Timing residuals. If the object arrives at predicted positions early or late by more than the observational uncertainty, that's evidence of acceleration. Even small, sustained thrust over weeks can produce detectable timing offsets. Orientation changes. If high-resolution imaging reveals that the object's rotation state has changed, say, its spin axis has reoriented, or its rotation period has sped up or slowed down, that could indicate internal mass redistribution or external forces acting on it. Comets do experience torques from outgassing jets, so this isn't by itself diagnostic, but combined with other anomalies, it would be significant. And here's the thing. None of these measurements require exotic technology. We can do them with existing telescopes and instruments. It's just a matter of observing time, coordination, and analysis. If 3i Atlas were following a designed itinerary, if someone or something planned, this trajectory, then the Mars and Jupiter encounters are waypoints. Checkpoints on a tour. You survey Mars in early October. You use the Sun's thermal energy during perihelion. You study Jupiter's magnetosphere in March. Each stop has a purpose, but if it's natural, then Mars and Jupiter are just dots on the map, random intersections of an interstellar trajectory with planetary orbits. Coincidences. How do you tell the difference? You watch, you measure, you test predictions. If the object behaves exactly as gravity predicts, with outgassing variations consistent with solar heating, then coincidence wins. If there are deviations, unexplained accelerations, structural changes, electromagnetic interactions that don't fit natural models, then the design hypothesis gains traction. And speaking of design, there's one proposal that's been circulating in both peer-reviewed journals and congressional letters. A proposal that could settle a lot of these questions definitively if it actually happens. A spacecraft intercept. Not just passive observation, but an active flyby mission. And the spacecraft in question. Juno. Part 10. The Juno Intercept Proposal and NASA's Dilemma. On September 20th, 2025, a peer-reviewed paper appeared in the journal Aerospace with a provocative title, Using NASA's Juno Spacecraft to Intercept 3i Atlas. The lead author was a trajectory dynamics researcher, and the paper laid out in meticulous detail how Juno could be retargeted from its current mission at Jupiter to conduct a flyby of the interstellar comet. It's not science fiction, it's orbital mechanics, and it's feasible. Barely. Let me walk you through the proposal, because it's both brilliant and audacious. Juno is currently in orbit around Jupiter, studying the planet's atmosphere, magnetic field, and interior structure. It's been there since July 4th, 2016, executing a series of highly elliptical orbits that bring it close to Jupiter's cloud tops once every orbit. The mission has been extended multiple times, and as of 2025, Juno is still operational and returning incredible data. But Juno also has a propulsion system. Specifically, a main engine that hasn't been fired since the Jupiter orbital insertion burn in 2016. That engine has been dormant for 9 years, but theoretically it still works, and it has propellant left maybe. The proposal hinges on a two-burn manoeuvre using Jupiter's gravity as an accelerator. It's called a Jupiter-Oberth manoeuvre, named after Hermann Oberth, one of the founding figures of rocketry. The idea is simple, but powerful. When you're deep in a gravity well, moving at high speed, a relatively small engine burn produces a disproportionately large change in your final trajectory. You're leveraging the potential energy of the gravity well to amplify your thrust. Here's the timeline the paper proposes: September 9th, 2025. Juno performs a close Peryov pass, closest approach to Jupiter, and fires its main engine at that moment. The burn would require a delta V of approximately 2.68 kilometers per second. That's significant. For comparison, the lunar module descent engine that landed Apollo astronauts on the Moon provided about 2 kilometers per second of delta V. So we're talking about a real, mission-class engine burn. That burn would send Juno onto a hyperbolic escape trajectory from Jupiter, heading toward the inner solar system. March 14th, 2026. Juno intercepts 3I Atlas at a relative velocity of around 19 kilometers per second. That's fast, too fast for orbital rendezvous, but perfect for a high-speed flyby. At closest approach, Juno would pass within a few thousand kilometers of the comet, close enough for its instruments to collect detailed data. What instruments does Juno have that would be useful? MIR, the Jovian Infrared Auroral Mapper. This is an infrared spectrometer originally designed to study Jupiter's auroras, but it could measure the temperature and composition of the comet's coma. UVS, the ultraviolet spectrograph. This would map the ultraviolet emissions from the coma, revealing the distribution of gases like carbon monoxide, water, and hydroxyl radicals. GIRAM, the Jovian Infrared Auroral Mapper. Another infrared instrument, this one optimized for imaging. It could map the thermal structure of the nucleus and coma. MAG, the magnetometer. Comets don't have intrinsic magnetic fields, but they do interact with the solar wind, creating induced magnetospheres. MAG could detect those interactions and, critically, could reveal whether the object has any anomalous magnetic properties. WAVES, the radio and plasma wave instrument. This could detect plasma oscillations, radio emissions, and electromagnetic activity in the vicinity of the comet. If the object were emitting any kind of electromagnetic signals, natural or otherwise, WAVES would catch it. Juno Cam, a visible light camera. Not a science instrument officially, it was included for public outreach, but it takes gorgeous images and could provide high-resolution photos of the nucleus and coma structure. So Juno is well equipped for a comet encounter. The problem isn't the instruments. The problem is the risk. Juno's main engine hasn't fired in 9 years. Spacecraft engines are finicky. Propellant can settle, valves can stick, seals can degrade. There's a non-zero chance that when you command the engine to fire, it doesn't. Or worse, it fires partially or erratically, leaving the spacecraft on an uncontrolled trajectory. If the burn fails, Juno would be lost. It wouldn't have enough propellant to recover, and you'd be throwing away a flagship mission that's still producing world-class science at Jupiter. The paper notes that the authors contacted the Juno mission team to inquire about propellant margins and engine health. The response, as reported in the paper, was cautious. The team acknowledged that propellant reserves exist, but conducting a major retargeting burn would require a formal mission review, risk assessment, and approval from NASA headquarters. There's no official plan to do this, but here's where it gets political. On an unspecified date in 2025, sometime after the paper was published, Representative Anna Paulina Luna, a member of Congress from Florida, sent a letter to NASA urging the agency to study the feasibility of using Juno for a 3I Atlas intercept. The letter emphasized the scientific value of in situ measurements of an interstellar object and the unique opportunity presented by the timing and geometry. Congressional nudges like this matter. They don't guarantee action, but they signal political interest, which can unlock funding and priority. If Congress is paying attention, NASA has to at least respond. As of now, there's been no public NASA commitment to retarget Juno. The agency has not announced a mission plan, but the fact that a peer-reviewed trajectory study exists and that Congress is asking questions means this isn't just an academic exercise. It's a real possibility, however slim. What would the scientific upside be if it happened? Huge. Unprecedented. We've never had a spacecraft intercept an interstellar object. Oumuamua came and went before anyone could organize a mission. Borisov was observed remotely. 3i Atlas is the first interstellar visitor where we have enough warning to potentially launch or retarget a mission. An intercept would give us direct measurements of the nucleus size, shape and composition. It would resolve whether the headlights are real or observational artifacts. It would map the magnetic and plasma environment. It would detect any electromagnetic emissions. And critically, it would provide imagery at resolutions that telescopes simply cannot achieve. If 3i Atlas is artificial, a Juno flyby would probably reveal it. You'd see structure. You'd detect anomalies. You'd get data that couldn't be explained away. If it's natural, a Juno flyby would still be transformative. We'd learn about interstellar comet composition, outgassing mechanisms and the physics of objects that have spent eons in the cold dark between stars. But there's the risk calculation. Juno is expensive, billions of dollars over its lifetime. It's a working mission at Jupiter. Do you gamble that on a risky one-shot intercept with an object that might just be a weird comet? NASA's decision-making process on something like this is Byzantine. It involves mission scientists, program managers, headquarters leadership, budget analysts, and ultimately political considerations. The fact that Congress is involved suggests there's interest, but interest doesn't guarantee action. What should we watch for to know if this is actually happening? Mission updates. If NASA announces a trajectory correction maneuver for Juno, or if there are changes to the mission's Perijove timeline, that's a signal. Spacecraft retargeting requires months of planning, so any movement would need to start soon. Propellant budgets. If the Juno team releases updated information about propellant reserves and engine health, that's a clue they're seriously considering it. Scientific advocacy. If major planetary science organisations like the American Astronomical Society's Division for Planetary Sciences start publicly advocating for the intercept, that adds pressure on NASA to act. And here's the final twist. If Juno doesn't intercept, we're still not out of options. ESA's JUICE mission, Jupiter Icy Moons Explorer, launched in 2023 and is currently en route to Jupiter. It won't arrive until 2030, long after 3i Atlas has left the inner solar system, so JUICE can't intercept. But other missions could be proposed. Fast, lightweight probes designed specifically for interstellar object encounters. The technology exists. The question is political will and funding. The Juno intercept proposal is a case study in how science and politics intersect. It's also a reminder that we have the capability to do extraordinary things when we choose to. The question is, will we choose? For now, Juno continues its Jupiter mission. 3i Atlas continues its inbound trajectory, and the clock ticks down towards solar conjunction. Which brings us to the moment we've been building toward. The blackout. The gap. The period when Earth goes silent and 3i Atlas disappears from view. What happens during that unseen window could change everything. Part 11. The solar eclipse window. Imagine standing in a dark room, watching a stranger walk toward a corner. Just before they reach it, the lights go out. You hear footsteps. You hear rustling, maybe the creak of a floorboard. And then, a minute later, the lights come back on, and the stranger is standing in a slightly different spot. Did they move deliberately? Did they do something you couldn't see? Or did they just naturally walk to where they're standing now and the darkness was incidental? That's the situation we're about to face with 3i Atlas. Let's build the timeline in detail because the geometry of solar conjunction is the entire point. Starting in late October 2025, likely around October 25th, the angular separation between 3i Atlas and the Sun, as seen from Earth, drops below approximately 50 degrees. That's Hubble's sun avoidance limit. Hubble can't point anywhere near the Sun without risking thermal damage to its instruments, so Hubble goes dark on this target. By October 29th, perihelion day, the comet is directly between Earth and the Sun in terms of ecliptic longitude. Not exactly in front of the Sun, the geometry isn't a perfect eclipse, but close enough that the Sun's glare dominates. Ground-based optical telescopes lose the object in the solar halo. This blackout period extends into late November. The exact date when observations become possible again depends on the Sun-object-Earth angle widening back beyond the safe viewing threshold, but ESA has indicated late November as the re-emergence window. So we're looking at roughly 4 weeks. 4 weeks where the most interesting interstellar object we've ever tracked is unobservable from Earth. Now, let's talk about what we can't see during that time, and what we might still detect indirectly. What we lose: visible and near-infrared photometry. No brightness measurements, which means no tracking of outgassing activity, No monitoring of brightness variability. No light curve data. Spectroscopy. No spectra means no composition measurements. We can't track changes in the carbon dioxide to water ratio. We can't watch for the emergence of ion emission lines. We can't detect new molecular species in the coma. Astrometry. No position measurements means we can't refine the orbit. If the object accelerates, if there's any non-gravitational force acting on it, we won't see it happen. We'll only infer it afterward from positional residuals. High-resolution imaging. No chance to resolve structural details of the nucleus or coma morphology. What we might still detect, Mars orbiters. Mars Express and Trace Gas Orbiter have a small window around October 3rd before conjunction fully sets in. If they capture data, it'll be transmitted back to Earth and analysed over the following weeks. But that's early in the conjunction window, not during the deep blackout. JWST geometry. The James Webb Space Telescope sits at the L2 Lagrange point, about 1.5 million kilometres from Earth on the side away from the Sun. Its sunshield protects it from solar heat, but it also constrains pointing. JWST can't look toward the Sun. There might be narrow geometric windows where JWST could observe 3i Atlas during conjunction, depending on the object's ecliptic latitude and JWST's orbital position, but those windows would be brief and suboptimal. Don't count on JWST data during the blackout. Coronagraphs. The SOHO spacecraft and other solar observatories carry coronagraphs, instruments that block the Sun's disk to study the corona. These can detect comets passing very close to the Sun, but 3i Atlas isn't passing close enough. Its perihelion of 0.96 astronomical units puts it well outside the field of view of most coronagraphs, so no data from SOHO. Classified sensors. Here's where we enter speculation territory. The United States Department of Defense operates a constellation of infrared early warning satellites designed to detect missile launches. These satellites, part of the Space-Based Infrared System, or SPIRS, are sensitive to thermal signatures. If 3i Atlas were to execute a large hot thruster burn during conjunction, those sensors might catch the infrared flash, even if ground telescopes can't. Would that data be made public? Probably not immediately. Classified systems protect their capabilities, but information can leak. Papers get published years later. Whistleblowers talk. If something big enough happened, we might eventually hear about it indirectly. So we have limited indirect options, but nothing remotely close to the continuous monitoring we've had up until conjunction. Now let's game this out. What could happen during the blackout that would be significant? Scenario 1, nothing. The object continues on its predicted trajectory, outgassing naturally, behaving exactly like a comet should. When it re-emerges in late November, its position matches gravitational predictions within observational uncertainty. Its brightness has evolved as expected. Water vapour has increased, dropping the CO2 to H2O ratio. Ion emission lines appear alongside nickel, consistent with heating. In this scenario, the blackout was uneventful. The silence held no secrets. Scenario 2, subtle manoeuvring. A small delta V burn, maybe a few meters per second, occurs during conjunction. This is enough to slightly alter the trajectory, but small enough that it might be disguised as outgassing thrust. When the object reappears, astrometric residuals are present, but they're borderline. Teams argue over whether it's real or measurement error. The ambiguity persists. Scenario 3, deployment. The object releases secondary objects, probes, fragments, whatever, during conjunction. These secondaries follow slightly different trajectories. When observations resume, sharp-eyed astronomers notice faint companion objects trailing the main nucleus. Are they natural fragments from cometary breakup or deliberate deployments? Without seeing the event itself, it's hard to say. Scenario 4, structural change. The nucleus undergoes a significant transformation. Maybe it splits. Maybe a surface layer peels away. Maybe something unfolds. When imaging resumes, the object looks different. Different shape, different brightness distribution, different morphology. Natural comets do split, so this alone wouldn't prove artificiality, but combined with other anomalies, it would raise questions. Scenario 5, signal. During conjunction, the object begins emitting a narrowband radio signal or modulated light. Ground telescopes can't see it because of the Sun, but spacecraft elsewhere in the solar system, Mars orbiters, lunar satellites, deep space probes, detect it. By the time Earth's telescopes reacquire the object, the signal has stopped. We're left with second-hand reports and fragmentary data. Each of these scenarios is possible. Some are more likely than others. Scenario 1 is the default expectation. Scenarios 2 through 5 require increasing levels of something unusual is happening. The critical thing to understand is this. The absence of continuous observation during conjunction creates ambiguity. If anomalies appear post-conjunction, we'll never know exactly when they happened. We'll have before and after, but not during. And that gap makes definitive conclusions harder. It's the perfect time to manoeuvre, if manoeuvring were the goal, but it's also just an unfortunate coincidence of geometry if this is a natural comet. Prior cases where important events occurred during conjunction. Let's talk about a few. Mars Pathfinder, 1997. During solar conjunction, the lander and rover went into safe mode. No data transmission. When contact resumed, everything was fine, but there was a brief period of uncertainty. Voyager 2, 2020. A solar conjunction period coincided with the loss of telemetry from Voyager 2's primary antenna. Engineers had to troubleshoot blind using stored commands and predictions. Contact was restored, but it was tense. Comet Ison, 2013. This sun-grazing comet passed behind the Sun and disintegrated during perihelion. We saw it go in, we didn't see it during closest approach, and when it should have emerged, it was gone. The breakup happened during the blackout. We inferred what occurred, but we didn't witness it. In each case, the conjunction added drama and uncertainty, and in the case of Ison, it hid the critical event entirely. What will happen with 3i Atlas? We'll know in late November. If post-conjunction observations show everything is normal, we'll breathe a sigh of relief or disappointment, depending on your perspective, and move on. If post-conjunction observations show something's changed, we'll scramble to figure out what happened and when. The silence before the sun is upon us. The countdown has started, and when the lights come back on, we'll see what's really there. But here's the thing. Even during the blackout, someone might be watching. Eyes we don't control. Instruments we don't access. The question is whether they'll tell us what they see. Part 12. Hidden Eyes, ESA, JWST, and Classified Sensors. When I say we're blind during solar conjunction, I mean we, the public, the scientific community, the civilian space agencies operating in the open. But blind is a relative term in the modern era. There are other eyes, some of them we know about, some of them we don't. Let's start with the ones we know about. The European Space Agency has 2 spacecraft at Mars. Mars Express, which has been there since 2003, and the Trace Gas Orbiter, or TGO, which arrived in 2016. Both are primarily focused on Mars science, studying the atmosphere, mapping the surface, searching for trace gases like methane, but they have instruments that can be pointed elsewhere. ESA has confirmed that both spacecraft will attempt observations of 3i Atlas around October 3rd, 2025, when the comet passes within roughly 30 million kilometres of Mars. That's before the full solar conjunction blackout from Earth, but it's still a useful data point because Mars is in a different position than Earth. The viewing geometry is distinct. What can Mars Express and TGO actually see? Mars Express carries HRSC, the high-resolution stereo camera which can image invisible wavelengths, and Omega, a visible and infrared mineralogical mapping spectrometer. Omega could, in theory, detect emissions from carbon dioxide, water and dust in the comet's coma. HRSC could image the overall structure, though the resolution will be poor at that distance. TGO carries NOMAD and ACS, spectrometers designed to study Mars' atmosphere, but they're sensitive enough to detect cometary volatiles if the signal is strong. TGO also has CASIS, a colour and stereo imaging system, which could capture wide-field images of the coma. ESA has set realistic expectations. These aren't comet-hunting spacecraft. They're Mars orbiters being temporarily repurposed. The data will be marginal, but marginal data is better than none. Here's the catch. That data won't be released immediately. Space missions have data embargoes. Science teams get first access to analyse and publish. Public release often comes months later. So even if Mars Express and TGO capture something interesting on October 3rd, we might not hear about it until early 2026. ESA has also mentioned that JUICE, the Jupiter Icy Moons Explorer, might attempt distant observations in November 2025. JUICE launched in April 2023 and is currently cruising through the inner solar system on its way to Jupiter. Its trajectory and timing might allow a distant look at 3i Atlas during the Earth blackout period, but JUICE is far away, millions of kilometres from the comet. Its instruments are designed for close-up work at Jupiter's moons, not remote observation of comets. The data, if any, will be limited. ESA has indicated that results from JUICE, if they exist, might not be available until February 2026, so the public space agency eyes are few, distant and slow to report. Now let's talk about the eyes we don't control. The United States operates a network of classified space surveillance assets. Some of them are optical telescopes designed to track satellites and debris in Earth orbit. Others are infrared sensors designed to detect missile launches and nuclear tests. These systems are collectively part of the Space Surveillance Network, or SSN, and they're very, very good at their jobs. Could these systems detect 3i Atlas during solar conjunction? The infrared early warning satellites, ESPERS and its predecessors, are designed to spot the hot, bright plumes of rocket motors. A comet nucleus, at 1 astronomical unit from the Sun, is warm, but not rocket motor hot. It's glowing in infrared due to solar heating, but it's not producing a sharp thermal spike. So passive detection of the comet by ESPERS is unlikely, unless something unusual happens, like a thruster burn. If 3i Atlas were to fire a chemical rocket during conjunction, ESPERS would probably see it. The infrared flash would stand out. But would we ever hear about it? That's the policy question. ESPERS data is classified, its capabilities are classified, the locations and pointing directions of the satellites are classified. The Department of Defense does not routinely share this data with the civilian scientific community, and it certainly doesn't publish it in astronomical journals. But leaks happen. Information migrates. Sometimes classified observations are declassified years later for scientific purposes. During the Cold War, Air Force satellites detected meteor impacts and fireballs that later became public scientific data. There's precedent. If a major anomaly were detected by classified sensors, would the information eventually surface? Maybe. Probably not in real time, but possibly in the long term, especially if the anomaly was significant enough to warrant disclosure. And then there's JWST, the James Webb Space Telescope. We've already talked about how its pointing constraints make solar conjunction observations difficult. But let's dig deeper. JWST orbits the L2 Lagrange point, about 1.5 million kilometres from Earth, on the anti-sun side. Its sun shield is always between the telescope and the Sun, protecting its cryogenically cooled instruments. This means JWST can never look toward the Sun. It has a field of regard, a cone of sky it can observe, that avoids the Sun by about 85 degrees minimum, but the solar system isn't static. Earth orbits. L2 orbits with Earth. The Sun-Earth L2 geometry changes continuously. And depending on where 3i Atlas is in its orbit, there might be brief windows where JWST's field of regard includes the comet, even during Earth's solar conjunction. This is a complicated geometric calculation. It depends on the comet's ecliptic latitude, its position along the ecliptic longitude, JWST's orbital phase, and the Sun avoidance angle. I can't tell you definitively whether JWST will have such a window without running the numbers, but it's possible. If JWST does observe, the data would be gold. JWST's spectroscopic capabilities are unmatched. It could measure the carbon dioxide to water ratio with precision. It could detect trace molecules. It could map the temperature structure of the coma. But again, JWST time is precious. It's the most oversubscribed telescope in history. Getting observing time requires a successful proposal months in advance, or a director's discretionary time request for targets of opportunity. Has anyone submitted such a proposal? We don't know publicly. Proposal information is often confidential until observations occur and papers are published. So the JWST question is, might it observe during conjunction? Possibly. Will we know immediately? Probably not. Which brings us to the broader issue. Data silence during conjunction could be a policy choice, not just a technical limitation. If something unusual were detected, whether by Mars orbiters, JWST, or classified sensors, the decision to release that information immediately versus holding it for analysis versus classifying it entirely is a human decision, not a physical one. Scientific institutions have protocols. Data goes through validation, peer review, and coordinated release. Space agencies don't tweet raw observations. They analyze, they verify, and then they announce. Military and intelligence agencies have different protocols. They classify, They compartmentalise and they disclose only when strategically advantageous or legally required. So if 3i Atlas does something during conjunction, and if that something is detected by any of these hidden eyes, the flow of information to the public could be delayed by weeks, months, or indefinitely. This isn't conspiracy theorising. This is just how information systems work. Scientific data has embargoes. Military data has classifications. The question isn't whether someone might see something we don't. The question is whether they'll tell us. What should we, as engaged observers, do with this uncertainty? Chase the open data streams first. When 3i Atlas re-emerges in late November, watch for position measurements from amateur and professional astronomers. Watch for spectra from observatories worldwide. Watch for announcements from ESA about Mars orbiter observations. Watch for any JWST data releases. Don't over-index on secrecy. The vast majority of solar system science happens in the open. Classified sensors are optimized for Earth-focused threats, missile launches, satellite maneuvers, not interstellar comets. The odds that classified systems have unique, decisive data about 3i Atlas are low, but stay aware. If months after conjunction, a paper appears with data that couldn't have come from public observatories, ask questions. If informal reports from mission scientists hint at interesting findings that aren't yet public, pay attention. Information leaks. It always does. The hidden eyes are there. Whether they're watching, and whether they'll share what they see, we'll only know with time. Thank you for joining me tonight. I hope you learned something new, and I will see you in the next one. Good night.